Hi everyone, my name is Christina and today I'll be presenting to you our recent work on patient-specific virtual spine straightening and vertebra inpainting, an automatic framework for osteoplasty planning. This is a joint work between Helmholtz AI, Sindhealth and the Technical University of Munich. Let's start off with an introduction. This is a spine. It's made up of 33 bones named vertebrae and is responsible for the main support of our body, allowing us to stand upright, bend and twist. If one of these vertebrae collapses, we have a case of a vertebral compression fracture, which causes severe pain, deforms the spine, and can also endanger more vertebrae from fracture. In severe cases, doctors may decide to perform surgery. Vertebroplasty is one of these, wherein a needle is injected into the vertebral body and cement is passed through it to stabilize the vertebra and restore its height. A common complication is cement leakage, which can occur due to an overlarge amount of cement being injected. We attempt to minimize these complications by proposing an automatic framework for osteoplasty planning. The inputs to this framework are the patient's CT scan and the fractured vertebra label, and with these, the framework attempts to simulate the spine in its pre-fractured healthy state, finally outputting an upper bound for the amount of cement needed for injection. It consists of three main steps: segmentation, straightening, and inpainting. For the first step of vertebra segmentation, we re-implement Secubo-Yinez et al.'s three-stage approach and achieve state-of-the-art results. This involves a 3D localization unit for detecting the spine, the butterfly net for labeling the centroids of the vertebrae, and finally a 3D patch-based segmentation unit in order to acquire the final segmentation. The next step is spine straightening. Here, we attempt to restore the spine's curvature and height to match that of a healthy-looking vertebra. For this task, we use a reference healthy spine. After acquiring its mask, we also use the fractured spine mask as inputs into our algorithm. We first select a region of interest around the fracture. Next, perform vertebra cropping, and from these, perform a per vertebra rigid registration. From here, we can then compute the displacement fields, which are finally compounded using linear blend skidding in order to acquire this final straightened spine. Here we see an example of our region of interest for a spine before a fracture, after a fracture, and after our straightening algorithm. And it immediately becomes apparent how space has been created around the fracture. Actually, we performed an ablation study which showed that our spine straightening algorithm increases the overall framework's accuracy from 83.9% to 96.1%. The next step is vertebra inpainting. Here we extend the network by Yu et al. By adapting the input and output layers of the network to also accept the segmentation mask along with the CT image. We then remove the fracture from the CT image and mask and train a GAN network to perform vertebra inpainting and generate a healthy looking vertebra in place of the fracture. In total, we train two 2D networks, and this is what you can see inputs and outputs of each here. So we use lateral slices and coronal slices. And finally, fuse the outputs of both in order to obtain our final inpainted volume, which gives us, as you can see from our results, an overall better performance. From the final segmentation mask, we can then go ahead and calculate an upper bound of cement needed for injection. Here you see some results. So on the left, we have the fractured spine, in the middle is the straightened spine, and finally the inpainted spine. You see, looking a bit closely, you see here an example of how after our straightening algorithm, space has been created around the fracture. And after removing this and performing inpainting, you see how the fractured vertebra, which is a biconcave fracture in this case, and is somehow compressed at the tops here and the corner of the vertebra, has been replaced by a healthy looking vertebra. To conclude, our final inpainted vertebra volume has an average error of 2.6 milliliters, while the average vertebra volume is 67.83 milliliters. We propose vertebra inpainting, an innovative approach which can find other applications, for example, in biomechanics. We also noticed during our evaluation that the vertebral processes reduce performance and are therefore working on automatically removing these from our calculations in future work. We also plan to extend our inpainting model, which is currently in 2.5D to 3D in the future to ensure better coherence across slices. And finally, our framework can hopefully in the near future help reduce the number of cement leakage complications. And with that, I would like to thank everybody involved in this project and thank all of you for listening. And I hope to see you soon during our poster session.